Okay, so this next question is Leetcode problem number 438, titled Find All
Anagrams.
Find All Anagrams in a String. And essentially, what this problem is asking you to do, say you have basically a longer string and a shorter string. You have to find all permutations of the shorter string inside the longer strings, or longer string. Meaning, let's say you have, do you want to explain one of the examples on there?
Sure. Here's the first example that they gave, which is, so I'll note in the last one we had S and T, in this one we have S and P. So S is our source string, the string that we want to find all of the anagrams inside of. And P is the anagram that we want to compare to. Reminder that, so I have three here, so my anagrams of P are going to be A, B, C, A, C, B. I'll write them out here just so you have somewhere to see what I'm saying. A, B, C, copy this a few times. I'll note that for anybody who didn't immediately figure it out, the reason I'm able to figure out what the anagrams are is I'm just doing the permutations of A, B, and C together. So A, B, C, A, C, B, A, B, A, C, B, C, A, C, A, B, and C, B, A. You're never going to find another permutation of these three letters together. So I want to find any of these in this. So I can go through this and say, well, I see a CBA right there. E doesn't do anything for me. BAC works. And then if I stare at that for a lot longer, I'm not going to find any more. So I say, okay, I have CBA at position 0 and BAC at position 6. And then I return an array with all of those positions.
Yeah, so basically the array is of the starting positions of the anagram, or the starting position in the source string of the anagram. Okay, so any constraints?
I think they give a size constraint somewhere. Yeah, not larger than big number.
Yeah.
The only real reason for the size constraints is for them to say, don't make your solution too inefficient, or it won't run in time. That's oftentimes what the purpose of size constraints like this are going to be in problems like this.
Yeah.
I'm going to note, second example has some useful information. If you didn't immediately glean it, because sometimes these problems are written in tricky ways where you can't get all the information, where some of the information might be hidden. This one isn't, but sometimes it is. In this example, there's three. One AB, and then BA, and then AB. I'll note that there's an anagram that overlaps there. The BA overlaps with the AB and the other AB. That just means that we're not guaranteed that all of our anagrams are going to be disjointed from each other. They could overlap, and that's fine. You just, if you weren't considering that as a possibility, you should be.
Sounds good.
Given that, so there's two ways I could go about this, and I'm going to do it the less good way first, because it builds off of this. I'm going to steal this entirely. Actually, no, yeah, I'm just going to steal this entirely. Ta-da! I have an anagram checker. Give it two strings. Are those two strings anagrams of each other? So this is sort of like a classic sliding window, sliding door problem, where you're looking at a range inside of a thing that moves over time. So if I put something here, P is the anagram I want to compare against. So there's probably actually a worse solution that still works for this, but I legitimately don't know how to think of it, and it's mainly just because I've seen I know that this has to be a sliding door problem, so it's the first thing my mind goes to. And there's probably going to be some more naive solution that still works. When you do enough problems like this, you sort of start seeing like similarities between them. There's enough overlapping concepts that you start just sort of jumping to certain conclusions.
Yeah.
So this is a sliding door problem. Specifically, P is my window size, and S is the thing I'm sliding between. So whatever the size of P is, let's say P is 3 like it is here. I'd look at MSD, and then SDN, and then NBL, and then BLK, so on and so forth, all the way through it in that sliding window size of 3 from the beginning to the end. and I'd compare each of those to see if it's an anagram of some sort. So what I want to do here is I want to slide through the string. So I'm gonna say what I want to do before I start programming it, because that sort of helps. I want to slide through the string looking at a window, as I just said. And for each of those windows, I want to send it at is anagram, if is anagram says it's an anagram, then I want to add it to my array that I'm going to return. So that means a few things here. I need to make an array that I'm going to return. Is it an int array? It's an int array. Int array return array equals new. Oh, I don't know what its length is going to be.
The method definition is actually asking you for a list of integers.
It's making for a list. Yes. Thank you. I was going to miss that. Does this have Java 8, so I don't have to describe this at all? I'm just going to do it anyway because it's not hard. For those who are confused at Java, Java does weird stuff sometimes. These angle brackets are basically saying this is some sort of like generically typed object where you can give it objects that it deals with. So when you have angle brackets like this, you can give it certain different types of objects that let it do its job. So if I didn't give it an object here, it'd complain at me. Usually, except in Java 8 Plus, which is actually like Java 8. Java 8's been around for like 5 years at this point or something. So I guess it's common enough that you can expect to see it. I believe there's a way to leave these empty and for it to infer what the type this has to be based on what I put here. In fact, I'm going to try that and see if it works, because if it does, then it's helpful information for people.
Oh, you put list twice. It should be the second one. The first one is an abstract class. List is an abstract class.
Oh, you're right. I need to get a type of list.
Yeah. Like array list, linked list is what we're looking for.
Called array list. For now. We're just playing with this to see if it works. No brackets? Yeah, you were right. It does work.
And I don't know if you need the integer there. I'm
100% confident I need the integer there. It doesn't make any sense. How would it infer the type if I don't?
Yeah.
What sorcery is this? That's the list I'm going to be using to return my the locations that I find. Now I need to go through the my sliding window. I is less than. So my window, the length of the thing that I want to go through is S, but I'm only going as far as P. Am I guaranteed? I'm not necessarily guaranteed that P is smaller than S. So let's catch that. Technically there'd be no anagrams of P and S if P is larger than S. So yeah, that I just return an empty string there.
Yeah, empty list.
An empty list, yeah. So if p.length function greater than s.length return that'll do the thing. Case if p too big, there's nothing here. Don't worry about it. Now I'm guaranteed that p is at least as small as s. Cool. I is less than. This might be a less than or equal to. I need to think about that because I could have an off by one error here if I do this wrong. Because I also want this to work in the case that p and s are of equivalent lengths. So let's start with I know I'm going to need an s.length in here. Typing is still hard. I'm just going to put that there because I know I'm going to need more stuff here in a second. This is not the end of this, though. So if I is less than s.length, it's going to go through s.length. If I is less than s.length minus p.length, if s.length is 2 and p.length is 2, then if I is less than 0. So what do I want to do in each window? In each window, I want to if I'm going to write this nested, and it's going to look really bad, and I'm probably going to break it out into individual statements instead. If is anagram P, I'm changing the order, I don't care. If anagram P and then some substring of S, so S dot substring I, if I give it I, does the substring make 1 character or 0 characters?
It's 1. 1 is inclusive, 1 is not. And I believe the start is inclusive.
Cool. Inclusive, exclusive.
Yeah.
So p dot length minus 1. What am I doing? I plus p dot length minus 1. Hey, I'd want to use brackets here, but also it doesn't matter because it just goes, it computes them left to right. So I'll add p dot length and then subtract 1. Double checking in my head that this works. If p is a 1 character thing, then what this will do is, let's say we're at I equals 0. 0, 0 plus 1 minus 1. So 0, 0, inclusive, exclusive. No. Inclusive, exclusive, 1, 1 would still give it a 0, an empty string, wouldn't it?
Yes, it would.
Oh, never mind. That's what I want. One curly too many. Yeah. One curly too few. If it's an anagram, add it to the return array. Return array dot add. Return array dot add. I. I think that works. Yeah. I'm going to submit this, and I'm going to make a change here. I'm going to describe some things, and I'm going to make a change here. Some things to note here. Faster than very few. Yes, there's at least one really, really obvious optimization that I know of to be made here. I'll say why. So the running time of this is not O of P or O of S. Actually, the running time here is O of S times P. Neither of those are constant values, so you can't drop them. So they both contribute to the running time. The reason for that is because this runs through the length of S, technically the length of S minus the length of P, but that's still the length of S as far as analysis is concerned. For each window in the length of S, it runs through the length of P and recompute and in that window and sees if it's the same as the bucket for P. Now, technically, that's also like times 2P. Don't care about that. Irrelevant. Drop that constant. So this is, not perfect. I can get this down to a single linear time of just the length of S. In fact, I'm about to. Okay, so I mentioned that this goes through S and then it goes through P for each time it goes for each thing in S. I need this. Stealing code. So this is going to serve the same purpose as it did before. I'm going to make a for loop here. Grab P, be gone. So what this does is it does exactly what it did before. It gives me my footprint for what P is. P is the anagram that I want to compare against. And then when I go through S, I'm going to have another footprint, you could say. I need to do so. I have a sliding window here, and I want to check in that sliding window. At that sliding window, I want to have the state of I'll call it an anagram footprint of my anagram footprint, or my frequency list. We brought that up before. I want to have my frequency list for that window, and then I want to, at that point, when I have that frequency list, check to see if it's an anagram, move the window, remove the character that's no longer in that window, and add the character that is now in that window. Obvious issue. Issue number one. That means I'm still only going through a certain number of these. So on the first one, I have to have pre-filled a lot of the characters.
Well, is there a way maybe you could do it without pre-filling?
Yes. I could instead actually iterate through the entire length of this, and fill each character as I get to it, and then once the window is sufficiently filled, or once the frequency list is sufficiently filled, then start checking against my other frequency list. Go through the sliding window. No, so I'm going through the sliding window. No. I need to pre-prime this. It can be I. Piri, not SRE. SRE. I don't know why I changed it before I copied it. So I described all the logic already, so I'm not really going to redescribe the logic except to just say what this does. I prime the S array with the characters that with all the characters except for the last character of the window of P. In a window of P size, I prime it with characters P-1. At I equals 0, I'm no longer looking at 0 here. I'm looking at P.
Well, starting at, yeah, P.
Starting at P. Hi. So now I'm changing this from starting at 0 to starting at P, and then going through S dot length. Quick changes like this carry so many chances for off by 1 errors. It's terrifying. If they're the same as each other, then I add. I shouldn't have removed this before, and I'm sad now. Dot add. I minus P dot length. Run. That makes sense. I don't have an SRE and P array. I have an SRE and P array.
Yeah.
This solution does technically work, but I'm maintaining 2 different arrays here, and it's a bit of a mess. This is both worse and not as elegant as the solution you're about to see, which if you haven't figured out the solution from the hints before, you'll see it in a second. So the idea with this one is instead of maintaining 2 arrays that I'm going to compare against, I'm going to create an array that has a count of all of the instances of the letters that I need, and then I'm going to decrement that same array every time I see a letter that I care about. So if for CBABC 80 blah blah, I'd have a 1 in the A slot, so 1 in 0, 1 at index 0, 1 at index 2, 1 and 1 at index 2, and then zeros throughout the rest of it. And so in the sliding window, when I see C here, I would decrement at index 2, so it'd go down to 0. And if I see another C, it'd go down to -1. Irrelevant. And every time I go through the loop, I compare, see if my array is zeroed, and then go to the next iteration. Which isn't entirely true, because when I go outside the range of P, I'm going to need to start adding characters back in as well. But this is still easier to debug, to debug and more elegant than the other solution. So I'm just going to switch to this now. So decrement, and then if I is greater than P dot, greater than or equal to. So the length of P is, let's say 2. I at 0 is good, I at 1 is good, but I at 2, that means I've moved the window by 1, so greater than or equal to. I need that. It's one line. I like brackets, though. Brackets are nice. If I is outside of p.length, then the window has started moving. The window is now full, and every time you're moving it, so you need to add things back in every time something leaves the window. So we'll just take this p at short I minus minus p.length changes to plus plus. Okay, so this doesn't. I mean, okay. Doesn't solve the problem perfectly, because we're still about to instantaneously make an array that's filled with zeros. Actually, I don't even have to fill it with zeros, because Java integer arrays start with zeros, but that's fine. Piri new int 26. P.length is going to be 1 larger than the size at once.
Yeah, so +1.
Off by 1 errors are a thing.
Yeah.
And this will be much closer to the 50% mark. 64%.
Yeah.
So I'm sure there exist even more optimizations that you could do here. And once you start getting to like bleeding edge optimizations, you start getting into sort of esoteric solutions.
Or
This basically looks to here is O of S.
So, Xavier, I just want to say thank you for coming on and doing this problem for me, or these 2 problems for me. I really do appreciate it. For you guys who are watching this, it's good to practice with somebody, because what you're thinking might be good, but somebody else could have a better solution or a different way of thinking about the problem. Whatever the case is, it's always good to see problems in different views and be able to attack them in different ways. So Xavier, thank you again, and good luck with your opportunity with Google. And that's it from that.